Welcome to Mrs. Z's Chemistry. In this video, we will begin our study of thermochemistry, where we will learn about the amount of heat either released or absorbed during physical changes, which are phase changes, or during chemical reactions. The heat that is being generated by the sun is by nuclear fission or fusion, which is not a typical chemical reaction. Imagine two hydrogen atoms fusing together or combining together to form one new atom. This atom would have two protons, which would mean the two hydrogen atoms turned into one helium atom. In order for this to happen, a lot of energy is required, but once it does happen, more energy is released than what was required. This amount of energy is then used to fuel the next fusion reaction. This is what we call nuclear fusion, and this is what is happening in our sun right now. The sun provides nearly 10,000 times the amount of energy that planet Earth needs each day. In this thermochemistry chapter, we will be discussing and learning about the energy released or absorbed in chemical reactions and physical processes, and not nuclear fusion. Let's start with some definitions. Energy is the ability to provide heat or do work. Work, in fact, has a scientific definition. It's the process of causing mass to move against an opposing force. A good example of this is one where you lift something off the floor. You are doing work. You are moving matter against an opposing force, which is gravity in this case. There are two types of energy, potential energy and kinetic energy. The water at the top of a waterfall has potential energy because of its position. The water is not moving down yet, and so it is not doing any work. But when it does flow downward through that waterfall and through generators, it then has kinetic energy, which can be used to do work. Just like we learned before about the law of conservation of mass, where mass can't be created or destroyed, only changed, the same is true for energy. The first law of thermodynamics is the law of conservation of energy, which states that energy can neither be created nor destroyed, only transformed. Thermal energy is the kinetic energy associated with the motion of atoms and molecules. Temperature is the measure of how hot something is. If there is less thermal energy, the substance will feel colder. Temperature has the variable capital T in equations. If particles in a substance are moving or vibrating faster, the average kinetic energy of the particle is higher and the object feels hot. If the particles in a substance are moving slower, the average kinetic energy is lower, and the object feels colder. Here is a great way that we can show on paper a hot substance versus a cold substance. The hot substance is usually pictured in a warm color such as red, and there are more circles or lines around the particles that are showing a fast or highly rapidly moving particles. The cold substance, or just relative colder substance, is often shown in a colder color, like blue, and there are less lines or circles around each particle, showing that they are moving slower. Heat has the variable Q and is completely different from temperature. I know that in everyday language we may think of heat and temperature as the same thing, but in science and chemistry equations, they are in fact two different things that are measured with two different types of units. Temperature can have units of Celsius or Kelvin or Fahrenheit, whereas heat has a unit of energy that we'll discuss later on. In this diagram, we can see that there are two substances, one that is hotter than the other one. Here's the hot one, and here's the cooler one. When the two substances touch, the heat will flow from the hotter substance to the colder substance. Just like how water always flows down a waterfall and never up the waterfall, heat will always flow from the higher temperature to the lower temperature. At some point, the two substances will become the same temperature, and we say they have reached thermal equilibrium. There are two types of chemical reactions, exothermic and endothermic. An exothermic reaction is one that releases heat. You can think of heat as being on the product side of a chemical reaction, as it is produced alongside the chemical products. Combustion reactions are great examples of exothermic reactions. When logs are burning on a campfire, the reaction is releasing energy in the form of heat that we can feel. An endothermic reaction is the complete opposite. Energy is absorbed during endothermic reactions. You can think of the heat is on the reactant side of a chemical reaction, as heat or energy is required for these reactions to take place. A great example of this is an instant cold pack found in most first aid kits. When you squish the pack, you are breaking the seal that was separating the two chemicals inside. One chemical is water, and the other is ammonium nitrate. When these two chemicals react together, they absorb energy from the surrounding environment, which is why your skin feels cold if you touch this cold pack. The chemical reaction taking place inside the pack is drawing energy from your body, leaving your body feeling cold. Here are the energy units. You can read the slide for the definitions about calories. The lowercase c calories right here is the amount of energy required to raise 1 gram of water by 1 degree Celsius. A capital C calorie is what we're used to on food packages, and it actually means 1,000 calories or a kilocalorie of the lowercase c calorie. The SI unit, if you remember from back in chapter 1, we learned that SI comes from the French meaning or phrase of international system of units. So the SI unit is the joule, Joule, and it's a capital J abbreviation. Don't worry about this exact definition right here about moving a 1 kilogram object a distance of 1 meter. We won't be using all of those funky units, but we will just be using the joule when we need to calculate heat. We'll also use this unit conversion here that converts the joules, 4.184 joules is equal to 1 calorie, the lowercase c calorie. And these are on the back of your periodic table. In the next part, for 5.1, we will learn how to calculate heat using a new equation.